Hey everyone, today I wanted to do a quick little Wolfram tutorial using the Mothball app. It now has its own inbuilt Wolfram calculator and it's a lot more user-friendly than doing it online, and to my knowledge it's just as accurate. So the jump that we'll be Wolframming today is the trapdoor to daylight sensor NICs from HPK, and let's just jump right into it. So the first thing you need to find when Wolframming any jump is your initial speed vector and angle. So I've got the strat from HPK here, and this is just HH facing from 17.073. Right, so we've got our initial speed and angle. So Wolfram uses the run tick speed, which is why we've done the run tick. And then we're going to use that angle later. We don't really need it here for now, but it will be helpful later. So just keep that one in mind. The next thing we need to find when we're Wolframming are our blockages. So let's get that here. I just know from this jump, we've got two X blockages and a Z blockage. So make sure to turn that one to Z. And let's find what they are in game. So for our X blockages, they are at 4.3, and this is one block minus one trapdoor. Like the distance we need to pass, a trapdoor, one block minus one trapdoor. So that'll be 1 minus 0.1875. So for our X blockages, that's going to be 0.8125 for both of them. And then for our Z blockage, this is going to be 1.6. So one block plus 0.3 on each side for our player's hitbox. The Z, it's only one constraint because we just need to find between which two ticks we need to pass this distance of 1.6. Right, so let's put that in, 1.6 here. Alright, so the next thing we need to do is find which ticks that we pass all of these blockages on. So let's get a clip. Alright, so you've got your clip now. It doesn't have to be particularly good, just good enough to find the blockages. So I'm pulling it up here. We start at the run tick, that's going to be tick 1. Tick 2, jump tick, tick 3. Oh, that looks like a Z blockage, 13.7. Yep, 13.7. So our first Z blockage is going to be tick 3. Because run tick, jump tick, first air tick, Z blockage. Negative 4.3, that was our X blockage, so that's going to be tick 4, 5, 6, 7, 8, 9, 10. And then on 10, we're going to have both our last Z and X blockage. So the X one, it doesn't really matter for this jump because as you can see, we're not even close to cutting that in time. Not even close, so 0.1 away, but you will need it for things like a pane to pane, so let's just leave that one in there anyway. And then the Z was also on tick 10. Now, if you remember, we are Wolframming with 12 ticks. That's just the default one, but we have -1 tier from the daylight sensor, same as 3BC, so just make sure to change this to 11 air ticks. And that should be it. We can just calculate it. Bang, here we go, that's our turn. But if you're looking, hang on, oh no, that's within the inertia cutoff. 0.005 divided by 0.91. It's a little bit below that, so we're going to need to change some things to make this work. So yeah, we can do Inertia Avoid or Inertia Hit. Let's go with Inertia Avoid just because we're already so close to it. So we'll need to add another constraint here, and we're hitting inertia on X, so leave this on type X, and we'll just call it inertia. Let's see, which tick? 1, 2, 3, 4, 5, 6, 7, 8. All right, between tick 8 and tick 7, we need it to be less than negative 0.005 divided by 0.91. Since this isn't a perfect replica of Minecraft physics, I do like to add, maybe an E-5 difference just to make sure it is actually hitting inertia. So now let's recalculate it. Here we go. And now you can see it has now done that. Let's look at our velocity. Yep, it's above the inertia threshold. And our offset has dropped to about 0.005, but this should work within Minecraft. Right, so we have a working solution here. But if you have a look, this is our preturn and this is our jump angle. We know we're preturning because this first angle doesn't match the vector angle we gave Wolfram. And then the jump angle, this is the exact same as the facing, 16.53, 17.07. So we are getting a 0.5 degree jump angle. And if you've ever done this jump on HPK, you know it doesn't need a jump angle. So let's see if we can try and force it to do no jump angle and no preturn, just because that's what we like doing as humans. So we'll get a preturn label and a jump angle constraint, or a preturn constraint and a jump angle constraint. Turn these to F and put the preturn on tick 0, the jump angle on tick 1, make them both equals. So we want it to be the preturn the same as our vector angle, and the jump angle the same as our in-game facing, 17.073. So let's recalculate it. 0.809, that's roughly 0.0033 offset here. And as you can see, same vector angle, same jump angle. So we don't have to worry about that at all. No preturn, no jump angle. Now for the turns, we can check if it matches with what we get in game using Mothball. Mothball is a perfect recreation of Minecraft physics. This isn't, so let's just see if it works. See if we've done anything wrong. We're not turning on the jump angle, that's 0. For the first air tick, we're adding W and A. So in Wolfram, it doesn't know what that means. We just told it we're gonna add 45 degrees, but that's adding W and A. So this is actually only a 1.213 degree turn. Add 45 from that. And then for the rest, since we're already holding W and A, we don't need to compensate for that anymore. And we can just copy paste the rest of these values straight in. And if these both match, we should have a position that roughly matches this. And this is just verifying that our solution does work. Ooh, forgot to put that at the end. There we go. Yep, 8092, 80918. So not perfect, but good enough. With a bit of working with the angles a bit, you'll be able to change it and we'll be able to get a working solution. All right, so we found the offset for Inertia Avoid, but now we want to see what happens if we hit inertia, because it might be a little more optimal. So to change that, we'll need to change our inertia constraint. So right now it's barely avoiding it. Let's change it to barely hitting it. So we would want it to be slightly above the lowest amount you can hit inertia by. So we'll change this, instead of 501, we'll change it to be 0.0499. And we want it to be larger than that, because it's trying to get as low as possible, and it's just going to say, all right, I'll get just above 0.00499. And just above it, that's just barely hitting inertia. So we'll recalculate with this, but just before we do that, we'll need to change, because when you are doing inertia, drag gets set to 0. So we need to find which tick we're doing it on. Tick 7 it was. 1, 2, 3, 4, 5, 6, 7. Let's turn this one to 0. So our drag x is 0 on the 7th tick. Recalculate. So as we can see, we've now got a new solution. This is also for no preturn, no jump angle. It's only 0.002 offset, as we can see here. 8125 minus 8105, 002. So that's how we've just compared really quickly. Oh, inertia avoiding is actually better than inertia hitting on this jump. Right, now let's turn this back to inertia avoid, because as we saw, that is actually a little bit stronger for this jump. Turn all of these back. Calculate. Right, yep, that's what we had before. But how do we know this is actually the optimal facing? Well, we don't. So let's just get rid of all this for now, because we're going to be changing our turn probably. But let's say we try it with f17.05. This is how you find your optimal facing. So you change the angle, put this one in, match it, 17.05, and we're just going to keep going and try get this number as low as possible. So it's gotten smaller. Oh, 17.05 is better than 17.073. And actually, you see how we're still getting a small last 45? A 0.6 last 45 isn't really realistic. So let's add a last 45 constraint now. So this is going to be on tick 2, and we want this to be the exact same as our facing minus 45, just because that's what it was. It was always minus 45 from whatever we had before. And let's lower it even more. Let's see if we can find an even more optimal angle. 808.54, and it's changing by so little now. You can tell this is roughly the local maximum. So the most you can do this jump around 0.0004. So now it's finally time to put our macro in game. So we've changed it. We're now at no last 45, no JA, no preturn. Let's see if we can get these angles in game. So that's what? 9, 7. Let's just put these all up here. We could turn Q it, but we've already seen that these solutions are valid. Uh-oh, we're hitting the wall. So let's see if we can figure out why. Well, it's actually because, like I said, this isn't a perfect recreation of in-game physics, so we will have to add just a little bit more leniency on the first cut. Let's just do 0.57. Recalculate. All right, 9.5. The same turn with 9.5. Oh, and now it's not hitting inertia. So let's just change the angles a bit more. We're not avoiding, and there we go. 0.0038. We've successfully Wolframed this jump. It could be a little more optimal. You know, like I said, you do have to change the angles a bit around just to make it work. But that is roughly what we get here. Wolfram's predicting roughly 375, 38. You know, it's almost perfect. If you really want to optimize your angles, you can make it perfect, but there you go. That's an almost perfect turn for this jump, and that's how you Wolfram using Mothball. Thanks for watching.